7.4, arcsine, arctangent, arccosine, and trigonometric functions. And our essential question is, how do you find solutions to equations involving sines, cosines, and tangents? So far we've done this with cosines, and we used Arccosine, and we're going to extend this to sines and tangents. So let's start with what we already know. So we're going to recall cosine inverse of 3/5, for example, this is just an example, means any angle whose cosine is 3/5. What we learned in chapter 6 was that I could think of this as Arccosine of 3/5, which was the same thing as cosine inverse, right? But the only thing that we did differently when we changed it to cosine inverse was we said, well, it was going to either be the positive or the negative cosine inverse of my ratio plus every revolution afterwards. Okay, so let me show you why this holds true, looking at it in the coordinate plane, thinking circularly. So okay, so cosine of an angle is adjacent over hypotenuse. And we know that cosine is positive, so let's think about that. Cosine positive in quadrants 1 and in quadrant 4, right? So I know that if I have a positive cosine in quadrant 1, then that tells me that adjacent must be 3 and hypotenuse must be 5. And cosine is also positive in quadrant 4, which means I've got another angle here with 3 and 5 as my hypotenuse. So basically here I have two angles. I have the one that's opening counterclockwise and the one that's opening clockwise. This is going to be my negative and this is going to be my positive. So here I'll just draw that in. So this is cosine inverse of 3/5. But this one here is the negative cosine inverse of 3/5. And then I can do any revolution or any 360 revolution, or if we're talking about in radians, then it would be 2 pi revolutions. So we call the cosine function opposite pairs. Because basically you can see that we have the positive cosine and we also have the negative cosine, or the negative angle that creates, sorry, I misspoke. We have the positive angle and we have the negative angle that creates both of these cosine ratios, giving us the fact that arccosine is always the positive or negative cosine inverse of whatever our ratio of sides are, plus however many revolutions we want. Okay? All right, so then let's think about this in terms of sine. So now we're going to extend this to sine. So sine inverse means, or sine inverse, I'll use 3/5. I'll use 3/5 this whole time, just to give you an example. Means any angle whose sine is 3/5. So let's think about this. Well, sine is positive. Actually, I'll just put a little plus sign. Hopefully, if you don't understand what I'm saying, then you should write this out. But sine is positive in quadrants 1 and quadrants 2. Okay, so when I think about this circularly, and I'm not saying that, you're always going to have a positive ratio. You might have a negative ratio, and then you have to think to yourself, where is sine? Sine of which angle will give me a negative output? And those are going to be in quadrants 3 and 4, right, if we're talking negative. Here I'm just using as an example what they did in the book, which I really like, and I can only give you so many examples here. Okay, so I know that for my sine ratio to be positive, that means that my y values have to be positive. So that's going to happen in quadrant 1. and sine is opposite over hypotenuse, so this would be 3 over 5 here. 3 is my opposite, 5 is my hypotenuse, and then it's also going to be positive in the second quadrant, and again, opposite over hypotenuse. So what I'm thinking about now is I'm thinking about my initial angle here, and the supplement of that angle, that basically goes to the terminal side of that reference angle. So this is that reference angle, which is going to be the exact same as whatever this is. So if we're being exact about this, sine inverse of 3/5 is approximately 36.87 degrees. I'll use that just to kind of help us make some sense out of this. So this angle right here is 36.87 degrees. Well, so is this angle right here, right? They're both reference angles. Okay, so we can say that, well, one of the angles where sine of that angle is the ratio 3 over 5 is 36.87, but the other one is the supplement of that. Okay, so this angle right here, let's see, how can I do this? How about here? That big angle right there is really going to be 180 minus sine inverse of 3/5, which approximately gave us 143.13 degrees. So you see how I can find these two separate angles, and then I can find any revolution after that. So we can say then that arcsine of 3/5 really is the sine inverse of 3/5 plus 2 pi n, or it's the supplement of that, 180 minus sine inverse of 3/5 plus 2 pi n. Okay, so for sine, we think of these as being, where cosine were opposite pairs, we think of sine as being supplementary pairs. Let me get on the board. I always draw these out as I'm solving these equations. It makes a lot more sense to me to see them like this than to just sit here and memorize this. This confuses me a little bit. So just being honest with you, if I were you, I would draw this stuff out, but you can also just go with memorize the formulas. All right, so the one we haven't talked about then is tangent. So we can say that tan inverse of 3/5, what we're looking for is any angle whose tan is basically 3/5. Okay, so if we're talking about tangent here, in this scenario, we're talking about it being positive. Okay, so where is tangent positive? Well, it's positive in the first and the third quadrant, right? Basically where the signs are the same. So we know that tangent is positive in quadrant 1 and quadrant 3. Those are 180 degrees apart, right? So they're basically a half of a revolution apart. So if I think about 3/5, tan is opposite over adjacent. Okay, so I'll end up with this angle right here. But I can also have it tangent be positive over here, right? If this was -3 and -5. So in that case, we're talking about starting at the positive x-axis and going all the way around to the terminal side. Now again, these two angles here are congruent, right? They're reference angles. Okay, so whatever that is, if I take tan inverse of something, I haven't done that, so let's see. Let's make sure I'm in degrees. I am. And this could happen in radians too. So this angle here is about 30.96 degrees. So let's see, how can I do this? Let me just come here. So this angle here is going to be our tan inverse of 3/5, which is approximately, what did I say, 30.96 degrees. But in addition to that, I'm also going to have a half revolution more, right? I'm going another 180 degrees, or if I was talking about in radians, that'd be pi. So then this angle here is going to be our tan inverse of 3/5 plus an additional revolution, 180 degrees, or again, if I'm talking about radians, then I'd use pi. Okay, so we can say that these are a half revolution apart. And what we can finalize then is that arctan of 3/5, this one's actually kind of easy, is going to be the tan inverse of 3/5 plus 180 n, however many half revolutions I want to do. Okay, so important information here that you really want to get down. You want to be able to draw these. You want to be able to understand all this, but really, these are kind of your patterns. And the reason that they're patterns is because, you know, depending on what kind of pairs they are. And you already know this one, but we'll go ahead and box it out anyways. And like I said, I'm always going to draw. I'm not going to not draw. So let's see where my example one is. Solve 10 sine of x minus 0.2 equals -3. And we're going to do this algebraically. In the domain, and then we can verify our solutions. Graphically. Okay, so taking our original function that I was given, let's get sine all alone, so we're going to divide by 10. -3/10 is really 0.3, so I'll just use that. Okay, from there we're going to want to arcsine both sides so that we can undo this sign. So if I do that on the left side, I get x minus 0.2, and on the right side I get arcsine of -0.3. Okay, well in this case, where is sine negative? That's what we have to ask ourselves. Sine of what angle is going to give me a -0.3? And we know that sine is negative wherever the y value is negative. So that's going to be in quadrants 3 and 4. So just drawing myself a little picture here. So thinking about these are both going to be here. All right, so I'm going to go ahead and figure out what sine inverse is, just so I can have a really good idea about this. So sine inverse of -0.3 gives me, oh, I'm in degrees. How do I know that I should be in radians? If I look here, this is in radians, right? So my domain is telling me, hey, you need to be in radians. I'm in degrees, so I better change my mode. And you're going to have to be careful about this. You just have to constantly think about it. All right, trying that one more time. So sine inverse of -0.3 gives me -0.3. So I know then that I'm talking about this angle here, which is -0.3. It's really -0.305. or just a reference angle of negative 0.305. Now, if I think about this other angle then, what do I need to do to it? I'm going to need to add 180, right, to 0.305. This is my reference angle. This angle right here is also 0.305. Okay, so going on to my next step, I'm going to basically get x by itself by adding 0.2 to both sides. I'll put 0.2. Plus, and now instead of arcsine, I'm going to say sine inverse of negative 0.3 plus however many revolutions I want. And because we're in radians, I'm going to do 2 pi n. Or it's also going to be, remember I said that I can then take 180 and add to it that 0.305. Okay, or in this case, because originally I got a negative, I can say let me take pi and subtract negative 0.305, which really is like adding. Okay, so just remember that sine is supplementary pairs, and that's why we're basically subtracting it from 180 or from pi. So I can take this and say pi minus sine inverse of negative 0.3 plus however many revolutions I want. Okay, so getting the value here, I know that this amount right here ends up giving me negative 0.305. So this right here then is going to be pi minus a negative 0.305, which gives me approximately, so this piece right here is approximately 3.4, how about we go 7. Now let's go back to what I originally needed. My domain needs to be in between 0 and 4 pi, so it needs to be positive. So if I just start out by going 0.2 plus negative 0.305 and do no revolutions, I'm going to have a negative. My next highest value will probably come from this, where I don't do any revolutions. So let's see. Maybe just for now, maybe it might be a good idea if I actually do that. So 0.2 minus 0.305. So from these values here, I get negative 0.105. Now that's not an okay answer, but then let's add a revolution to that. So I'm going to add 2 pi to that, and I get 6.178. And I'll add another revolution to that. Just adding 2 pi gives me 12.461. Now the question to me, so I know that 4 pi is somewhere around 12. So I'm wondering, is this too big? So when I think about 4 pi, put that in my calculator, 4 pi is actually 12.57. So that might be good to know. This is 12.57. So I'm still in my domain with 12.461. But if I add another revolution to that, I'm not going to be. Okay, so we're going to stop there, knowing that I'm going to throw out this negative one. Okay, and then let's see what I get from this. So I've got, just if I do 0 revolutions, I'm going to have 3.647. I'm going to add 2 pi to that. 9.93. If I add 2 pi to that, I think I'm going to be too big. Yep, I end up with 16.213. Okay, that's bigger than that 12.5 that we were talking about, so I'm going to get rid of that one. So my final x values that are actually in my domain are 3.647, 6.178, 9.93, and 12.461, putting them in ascending order. And so these would be my final solutions. Okay, our second and final example for this video. We'll have more in this section, but I just want to cover a little bit at a time because this stuff can be kind of complicated. So we're going to solve for tan of 2 theta equals -5. So keeping an idea right now that I'm using theta, which means I'm going to be in degrees. For the first 3 positive values of theta. Verify graphically. Oh, I didn't verify the last one for you guys graphically. I apologize. Let's go back to that. I think I have this in my calculator. It's pretty easy. Basically, what you're going to want to do is you're going to type in into your y1 and y2. So this part right here would be y1, and this part right here would be y2. And then you'll find all the places where they intersect. So let's see what I've got here. So they're already typed in for us. Okay, so I can see that the first time that it looks like they intersect is approximately 3 point something. And I can go in and use my intersect feature to actually figure this out. But 3 point something, and we have 3.67. The second time where they intersect, it looks like it's approximately 6 point something. And again, we got 6.178. The next time where they intersect is approximately, looks to me like 9 point something, and actually almost 10, and this one is 9.93. And then the last one that we got was, looks like around 12 point something, and we did get 12.461. So again, you can use the intersect feature, but you don't have to as long as you can approximate that. Okay, so that's what it means to verify graphically. Alright, so I'm going to start by solving this. Or I'm going to solve it partially, you'll see. Then we'll talk about whether it's positive or negative. So I'm going to divide both sides by 4, so I can get tan by itself. That's the goal. So I get tan of 2 theta equals -5/4. So now I need to think to myself, where would tan, right, tan of whatever this angle is negative. So where would tan be negative? Tan will be negative anywhere where the two signs are the opposite. So that leaves me with quadrant 2 and also quadrant 4. So what's going to end up happening is this angle will be probably what I find. It's going to be a negative angle. And then I know that I'm half a revolution away to get to my other angle. Now this one's a little bit tricky because you have this double angle. Okay, so let's go a little bit further and then I'll talk a little bit more about that. So getting this double angle by itself, I arctan both sides. Well, arctan really means take whatever angle you get here, right, the tan inverse, and add a whole nother, I should have gone here. From where the terminal side of that angle is, you're going to want to add a whole half of a revolution, 180 degrees or a pi. Now I'm in degrees here, so I'm going to be adding 180 degrees. So I'm going to take 2 theta, and I'm going to go ahead and turn this into cosine inverse. So this is cosine inverse of -5/4, plus a half revolution, however many half revolutions I want. Oh, why did I put cosine? I'm sorry, I'm super tired right now. Okay, so tan inverse. Okay. Well now, and you could have done that before. You could have divided by 2 here to both sides, and then you would have just needed to make sure that this whole side would get divided by 2 once you did instead of the arctan, you did tan inverse. So here I'm going to go ahead and divide by 2 because this is kind of tricky. This even fools me often. So I have to be really careful when I think about this, because normally I'm thinking, hey, I need to add 180 for every half revolution, but really that 180 is getting divided by 2, so I'm really going to be adding 90. Okay, so you're going to have a half of tan inverse of -5/4, plus you're also going to have a half of this 180, which really gives you 90n. That becomes a little bit more tricky. Okay, so let's go ahead and let's finish this up. So we're going to have theta will equal, well, let's figure out what tan inverse of -5/4 is. Oh, and I better make sure I'm in degrees. I'm going to have to really be careful with that. But I think you guys you're getting that. I think you've had a lot of practice with it. Okay, so tan inverse of -5 divided by 4 is that, but I need half of that. So really it's -25.67. Plus any 90 degrees that I want to add to that. Okay, so we're supposed to do the first 3 positive. So I think I'm definitely going to have to add at least 190 degrees to get positive. Okay, so we're going to get 64.33, let's call that. Add another 90 degrees to that. Now, if we hadn't had this double angle, then we'd be adding 180. Okay, but because we have this double angle, we have to half our half revolution. Okay. Hopefully I didn't confuse you with that. And then add another 90 to that. My brain's too slow right now, so I'm using my calculator to add. Everything's in ascending order. If you turn to page 360, you'll see pretty much everything that we just went over, and it's nice and solidified for you, or summarized, not solidified, summarized. So you've got your properties here, and these are kind of little shortcuts for thinking about what arcsine, arccosine, and arctangent actually mean. Okay, and that's in both degrees and radians, you can tell. And they even talk about, let's see, I think they talk about how they are. Yep. Inverse sines come in supplementary pairs. Inverse cosines come in those opposite pairs. And then inverse tangents come in pairs half revolution apart. Let's go over one more thing. We've talked about this in the past a little bit, but now we're going to really get your knowledge, so that way when you guys go off to college and your professor talks in many different ways, you'll have many different professors, and you just want to be familiar with all the terminology. So let's now talk about interval notation. In our first example, what we used was inequality signs to talk about intervals of our domain. But there's also set notation, and so I want to go over that with you. So we'll go ahead and we'll use what we were already using. Let's see. The things we already covered was like 0 to 4 pi. So we'll go ahead and we'll use that. Let's see, I thought I had made myself a nice note, but maybe not. Okay, fine. So we'll go from 0 to 4 pi. Where basically, if we were graphing this, right, we'd have solid dots on 0 and on 4 pi. So in interval notation, we would say x is the set, or x is included in the set, or here it says x and it is an element of the interval. Okay, so this could stand for is within the set, is an element of, many of those things. And I'm talking about on page 359. If you look on page 359 in your textbook, I'm basically going to go over something like this, where we talk about closed interval and an open interval. So once again, let's see. The symbol, this thing right here from set terminology, is used to show that x is an element of or is in the given interval. So we can write it something like this. Okay, so this is in set notation, just saying that x is an element of the closed interval from 0 to 4. Okay, so or 4 pi. So I'm going to go ahead and write that down on your paper for you so that you have some good information. And I'm not going to do these visualizations. Okay, I think that you pretty much understand what these mean. So I'm going to go over what these mean, how these are equivalent. Okay, so if we include our extremes, then we're going to use closed set notation. Basically, this means that x is an element in this entire set, including 0 and including 4 pi. However, what if I did this? Then we can say that x is an element, oops, of course I just copied what I did above. And now I'm going to use more like parentheses. Between 0 and 4 pi, we don't include 0 and 4 pi. So if this was a number line, you'd have open circles on these two values. You can also do like half open. So maybe I say, for example, like 0, let's see, x is in between 0 and 4 pi, where I'm saying that 0 can be included, so you'd have a solid dot on 0, but an open dot on 4 pi. 4 pi is not included, so x is an element between 0 and 4 pi. 4 pi is not included. Okay, so we call this a closed interval. We call this an open interval. And then we call this a half open interval. I'm going to do this. It doesn't matter what half you do, so these could have been switched around, right? If maybe I just had x greater than 0 but less than or equal to 4 pi, then these two would be switched.